Hey, nice. Well, hello everyone. Welcome to the IGS seminar. Thanks for joining. Tonight we have another set of three early career speakers, early career scientists speaking today. And actually they are all UK based and quite close to each other, which is nice. We do it the way we always do it. So we first hear the three talks and then we have the questions at the very end. If there is a question you want to ask and you're worried about forgetting or whatever, just put that in the chat and we will ask you to unmute at the end when we have time for questions. Okay, so I'll just start. We're going to start with Alex Bradley, if you want to start sharing your screen already. Alex is a postdoc at the British Antarctic Survey in Cambridge, and he focuses broadly on ice-ocean interactions, and he's particularly interested in how the geometry of ice shelf cavities affect melting and implications of this for the ice dynamics. And with that, I would say over to you, Alex.
Great, thanks, Rebecca. I hope you can hear me and see my cursor as well. Cool, so yeah, my name is Alex Bradley. I'm a postdoc at the British Antarctic Survey, and today I'm going to be telling you about some work I've been doing on the melt response of Pine Island ice shelf to calving events. So to set the scene, many of you will be aware that melting of ice shelves has been implicated in long-term changes to West Antarctica. And the way that I like to see this is by showing this picture from Hamish Pritchard's 2012 paper, which shows offshore colours are the temperature of the ocean in a red to blue colour scale, and onshore ice shelf colours are the thinning rates of ice shelves. And all you sort of want to take away from this picture is that regions where you have relatively warm ocean temperatures are highly correlated with regions of rapid thinning of ice shelves. And that's particularly the case in West Antarctica. And the mechanism for that is that ice shelves apply a back stress on the grounded ice that we call buttressing. So ice shelves restrain the flow of the grounded ice and therefore prevent it from flowing, reduce the speed with which it flows. And I can't think of a better way to explain it than to just take a quote directly from the paper, which is that increased melt is the primary control on Antarctic ice sheet loss through a reduction in buttressing, leading to an accelerated glacier flow. But this was the long-term average. If you look on a kind of more fine temporal scale, you see a slightly more complicated picture. So this picture shows you the blue and red sections show you some normalized temperature index for the last 80 or so years. And the black and green lines show you the ice flux from Pine Island in black and Thwaites in green. And what you see is that there are periods of rapid acceleration in ice flux, predominantly in the mid 2000s, and then regions where you have stagnation and even a reduction in the ice flux. And if you squint hard enough, you can convince yourselves that when the ocean temperature is warm by this index, then you have relatively high ice flux, and vice versa for cold periods. And for the purposes of this talk, what does warm ocean and cold ocean temperature mean? Well, if you take a profile of temperature as a function of depth, some way offshore in the Amundsen Sea, then you get a picture that looks something like you have warm water at depth and relatively cold water at the surface, which is separated by a reasonably sharp transition. And when you have a warm year, this picnic line that separates these two layers is relatively shallow in the water column, whereas when you have cold conditions, this picnic line is relatively deep. So when that picnic line is shallow, you have a thick circumpolar deep water layer, thick warm water layer, which means you would expect more melting of ice shelves, and vice versa for cold conditions. That simple picture is a bit more complicated for Pine Island because of the presence of a large seabed ridge under its ice shelf. So this picture that I've just brought up is from Pierre Detru's 2014 paper, which shows a slice taken through Pine Island and into the ocean offshore And the colors, so this shows you observed ocean temperatures and simulated ocean temperatures under the ice shelf for both 2009 conditions in the ocean and 2012 conditions in the ocean. And in 2009, there was a relatively thick warm circumpolar deep water layer, whereas in 2009, that layer was relatively thin. And you see that in 2009, warm water is able to spill over this large seabed ridge that sits beneath Pine Island, reach this inner cavity, and provide a lot more heat for melting. Whereas in 2012, that layer of warm water wasn't thick enough to penetrate across the ridge, and you had a much smaller total flux of ice. In particular, the total flux in 2009 was 120 gigatons, whereas in 2012 it's something like 60 gigatons. So quite a big difference. So what you want to take away is that the seabed ridge, in combination with the ice shelf, acts as a topographic barrier to the inflow of warm water. So that's one piece of physics. The second piece of physics is that Pine Island has undergone significant calving recently. And this is a really nice video from Steph Limit's 2020 paper, where he plotted the ice front position over the last 30 or so years. And what you see is the ice front position is reasonably constant up until about the mid-2010s, when there were several large calving events. And the ice front as of 2020 is about 25 kilometers downstream of that position. And we also think that there's the potential for further calving of Pine Island in future that's related to damage that has already occurred on the ice shelf. So what I've been thinking about is, how do these two pieces of physics combine? I know that the presence of the ice shelf in combination with the seabed ridge restricts warm water access, but also the ice shelf front has retreated significantly by calving. And so I've been asking the question, has past and will future calving relax this topographic barrier and significantly change melt rates? And perhaps quite importantly, there's a kind of theoretical feedback loop where I might have calving. If calving leads to increased melting, that might lead to a loss of buttressing of the ice shelf, therefore ice acceleration, enhanced shearing, and further damage, which might promote calving. So there's a potential for a calving melt feedback cycle. And I'm basically testing the first chain in this feedback loop. So what I've been doing is using numerical simulations in both idealized and realistic geometries. So this is my idealized setup. This shows you a slice taken in the meridional direction throughout the domain. It's uniform into the page as you look at it. And what I do is I use the ocean model MIT GCM to resolve the circulation in this domain, which features a seabed ridge and an ice shelf, for lots of different ice front positions, which are indicated by the blue lines. And by comparing the melt rate in this red box for each of those different ice front positions, I get an assessment of the melt response to calving. And I'm also going to do this for 3 different gap widths between the ridge crest and the ice shelf to get a sense of how the cavity geometry affects that picture. Okay, so in the 100-meter case, which is what I'm going to show you now, my melt rate in this red box as a function of how much I've carved looks something like this picture. So as I go from left to right in this picture, I'm effectively carving the ice shelf. And when I'm at the dashed line, then my carving front sits directly above the ridge. And there's lots to dive into that I don't have time to here, but 2 things to point out is, one, that you get a very strong increase in melt rate as the ice front approaches the ridge, with this maximum something like 75% higher than it is when it's a long way offshore of the ridge. And perhaps surprisingly, you get a quite sharp reduction in the melt rate when the ice front is retreated to sit above the ridge. And this was a bit counterintuitive to us. We expected that once the ice front reached the ridge, there would be much, much more warm water that's able to reach that inner cavity. And indeed, you do see that, but you find that there's also a reduction in cavity circulation that opposes that to ultimately lead to a reduction in the melt rate. These idealized simulations also reveal a strong sensitivity on the cavity geometry. So this picture is the same as the one I just showed. It's the inner cavity melt rate as a function of the carved length. But now that narrow gap case that I just talked about is in gray, and I've added a slightly wider gap in blue and then a slightly wider still gap in green. And once you get up to a 200-meter gap, you're basically getting no melt response to calving. So the green line is effectively horizontal. There's like a 5% variation across this curve. And in the blue curve, again, there's a bit more of a response, but it's not that significant. Okay, so for the last 5 minutes of my talk, I'm going to tell you about the other side of the modeling we've been doing, which is about realistic domains. So my Pine Island domain looks, on my experiments are kind of typified by this picture here. So what I do is I, again, use MIT GCM to resolve the circulation under Pine Island for lots of different ice front positions. And what I'm going to use is the 2009 ice front, this kind of purpley curve, the 2020 ice front position, this slightly bluer curve, and then 4 kind of hypothetical situations. One of which sits approximately where the seabed ridge is, which is indicated by this almost vertical black dashed line. And because of a peculiarity of Pine Island, which has a thick ice keel, what you find is that the inner cavity, or the region close to the grounding line, is split essentially into 2 different regions, which are approximately dynamically disconnected. And so what I've been doing is thinking about the melt rate in both a northern cavity and a southern cavity, which sit on either side of that thick ice keel. And one thing that's important is that this southern inner cavity sits inshore of a region of the gap which is relatively wide, whereas this northern inner cavity sits inshore of a region of the gap that's relatively narrow. And that's exactly what the inset shows, is that gap between the ice draft and the ridge crest. So in the southern box, the mean is something like 300 meters, whereas in the northern box, that mean gap is something like 120 meters or so. So the melt anomaly, this picture shows you in panel A, the melt rate when the ice front is at its 2009 position, and then the anomalies in each of the 5 further simulations. And so the melt rate in the 2009 case is quite similar to what we see in observations. The melt rate is, the highest melt rates are concentrated very close to the grounding line, with maximum melt rates of about 120 meters per year. And the majority of the shelf has melt rates that are below 20 meters per year. And then when we subsequently remove sections of ice, we get quite complex melt anomaly patterns. There's a lot to dive into here, but just a few things to point out is, firstly, that, when you take the ice front position to its 2020 position, you get only a small inner cavity response to melting. So that suggests that Pine Island, or at least regions of Pine Island that are ice shelf that are dynamically important, haven't been affected by recent calving in terms of melting. However, when the ice front is retreated to a position that's approximately above the ridge crest, then you get a very, very strong melt anomaly in the shear margin, which extends all the way to the grounding line, which is potentially important for ice dynamics. And then just one more thing to highlight is that once the ice front is retreated a long way beyond the ridge, you get a large reduction in the melt rate, this large blue anomaly. So slightly more qualitatively, you can look at the mean melt rate in each of these regions as a function of the carved length. And I've just defined my carved length as being taken along this blue line, which runs sort of along the center line of the cavity. And this north box, which I told you sits inshore of a relatively narrow gap, shows this characteristically strong increase in melting before a kind of saturation and reduction once the ice front is retreated beyond the ridge. Sorry, I should have told you that again. The black dashed line shows you when the ice front is approximately at the ridge crest. And that's qualitatively similar to what we saw in the idealized experiments. Whereas in the south box, the melt response is smaller, at least in terms of percentage change, once you note that the y-axis have slightly different scales. And there's some funky stuff that we don't quite understand that's related to we think is related to variability in the gap width. But it's largely doing the same thing as what the idealized simulations say. And you might have to squint a little bit, and I'm sorry about this, but if you look at the total melt rate and the inner cavity as that's the black line in this inset. And what you see is that after the calving event, which took the ice front to the 2020 position, there's an approximately linear increase in the percentage change in melting, which means that the melt rate in the combined inner cavity is always increasing with calving. And our simulation suggests that there'll be an approximately 10% increase in the inner cavity melt rate by the time the calving front reaches the ridge, which will happen at, in less than a decade or so if the calving maintains its present retreat rate. And that means that, because you always have if your mean melt is always increasing with calving, then that means that this first step in this theoretical calving melt feedback loop that I talked about earlier is never broken and poses the potential for a calving melt feedback in Pine Island. So that's all I had to say. Thank you for your time. Just to wrap up with a few key points. Melting of Pine Island ice shelf is sensitive to calving because of the combination of seabed ridge and ice draft. The melt response to calving has a strong sensitivity on the cavity geometry. This theoretical calving melting feedback loop doesn't appear to be broken in any of the simulations that we performed. And that suggests that calving might be an important contribution to the ice ocean sensitivity of West Antarctica. And we just submitted this as a paper. So if you'd like to read the preprint, you can do so. It's hosted on SOR. You can scan the QR code here. Yeah, thank you for your time. And I look forward to questions at the end.
Perfect. Thank you, Alex. That was really interesting. So we'll have the questions at the end, and we'll now move on to Astrid Zimmerman, who is a PhD student at Grenoble University and Swansea University. And she is developing a visco-elastic ice shelf model using open source programs. And with that, over to you, Astrid. You're still muted.
Can you hear me now?
Yes,
see me?
that's perfect.
Okay.
Yeah.
Okay, fantastic. So hello and welcome to my talk. My name is Astrid Zimmerman, as Rebecca already said, and I'm doing a joint PhD at Swansea University in Grenoble, Alpes, together with like Steph Comfort, Fabien Gillet, Emmanuel Lemeur, and Adrian Luckman as my supervisors. Today I will talk about the development of a viscoelastic ice shelf model, which I've been working on. And, it's working, okay. At first I will give a very brief introduction and then talk about a bit about Riolef, which I think is a good alternative as an open source program. After that, I will explain my model briefly and give some results depending on the time that is left. Well, as Alex said a little bit before, ice shelves are the floating tongue of marine terminating glaciers. They surround most of Antarctica, as you can see in this picture, like all these like gray areas are ice shelves, and they buttress glaciers, basically slow them down. Studies have shown that glaciers increase their velocity up to 8-fold if you remove the ice shelf in the front. So that means that ice shelves are quite important to understand. In terms of modeling, ice flow is often described as a viscous flow, but there are also some viscoelastic approaches. The elastic part is time dependent and only significant for a short time scale. This relevant time for the elastic part is defined by the Maxwell time lambda, which is the viscosity divided by the elastic modulus. And depending on the parameters used, ranges between 2.7 hours and 11 days. This might not be a relevant timescale for ice sheets, but there are several factors or processes affecting ice shelves within this timescale. For example, tides, waves, or the fast load changes like draining of meltwater ponds. To introduce the program a little bit, I have been working with, it's called Reolef. It is a programming environment for solving partial differential equations with the finite element method. It was specifically designed for rheology problems, as the name already suggests, and it comes in general with, or it consists in general of C++ libraries, providing for one, a data structure like data types for variables, and functions that allow the code expressions to be very similar to the weak formulation. As you might be able to see in this picture over here, it's like one line of code represents like one equation, which you would write down by hand. That makes it really easy to read. It also provides a large range of algorithms and solvers to perform those tasks. Additionally, it comes with a set of Unix commands for shell programming, and it supports visualization in GNU-plot and PowerView, which is quite powerful. The best of it all, it's free and it follows the GNU General Public License. The brain behind this program is Pierre Zaramito, who is an HDR at CNRS in Grenoble, France, and has been working on it, I think, for many years, if not decades. Below here, you see a link to the webpage of Reolef. It's quite complicated. You can just like search Reolef. In this webpage, it looks like this. You can download the program. You have an extensive online documentation to read. And it comes with many, many, many examples and a PDF with like explanations for all the examples. Coming to the linear visco-elastic problem I tried to solve, or I implemented. I will not go into deep equations here, but in general, the problem is usually built up by the equations for conservation of mass and conservation of linear momentum, where we assume ice is incompressible, hence the density is constant. Additionally, we need to define a constitutive equation describing the stress-strain relationship. Here, opt for the simple visco-elastic model, which is the upper convective Maxwell model, which consists of like a viscous and a elastic part in series, as shown in this mechanical representation. The constitutive equation for that writes that the deviatory stress is 2 times the viscosity times the strain rate minus the viscosity divided by the Young modulus times the upper convective derivative of the deviatory stress. This alone already shows this is not a trivial problem, but Pierre Zaramito again introduced an operating splitting algorithm in '94, which he called the Theta scheme algorithm, which basically splits the problem in a sensible way here in the Stokes problem and in the tensorial transport problem, and solves them separately over parts of the time step, as you can see a little bit here, which seems to work quite well, and well, I've been using it. For the model geometry, I followed, or I oriented myself on the ice shelf ramp by Grave and Platte, which is a two-dimensional geometry representing the ice shelf along the flow line from the grounding line to the calving front on the right, where the thickness at the calving front, the thickness at the grounding line is thicker than at the calving front. For the mesh, I choose a triangular mesh, and with equal amounts of elements per height or thickness, which changes gradually in size over the length of the shelf. For the boundary conditions, I define the top boundary is defined as freeboard with like 0 stress. At the upstream boundary, I defined no inflow velocity and a pinning point down at this point. And the right and bottom boundary is defined by the buoyancy force, which is defined by the density, the water density times the gravitation times the depth below seawater level. For parts that are underwater, for the part that is above water, I set it to 0. The depth below seawater level had to be adjusted or corrected for the displacement over time, which was originally suggested by Durand. The result of the viscoelastic model I have compared to a common linear viscous model using the Stokes equation and setting the bottom boundary to 0 normal velocity. The shelf parameters I've used was 10 kilometers length, 400 meters at the grounding line and 200 meters at the calving front. And I've forced, or I used a constant forcing, so I simulate steady state over a longer period. On the right, we can see the results of both of the models. In red, the horizontal velocity, and in blue, the vertical velocity. The lighter colors are the viscous results, and the darker colors are the viscoelastic results. They're quite similar, but you can see that the viscous model overestimates compared to the viscoelastic model, mainly near the calving front. But most interestingly, we can see in the vertical velocity of the viscoelastic model a damped oscillation, which is induced, which we would expect due to the bending momentum of the buoyancy force introduced by the buoyancy force at the calving front. Hence, we can assume that the model is working well. For the last 4 minutes, okay, I need to speed up. I also introduced a tidal forcing, started with like a simple tidal forcing, only a sinusoidal forcing with like different amplitudes and for different frequencies. The two frequencies are the diurnal cycle with like 25 hours and a semi-diurnal cycle for 12.5 hours. And I used the maximum amplitudes of 5 meters for each, and a realistic case for the diurnal cycle, the Rossi, and with like 0.7 meters amplitude, and for the Weddell-C with like 1.5 meters amplitude. In these graphs, which is a lot, on the top two graphs show the horizontal velocity over time, and the bottom two graphs show the vertical velocity over time. I've used the same scale, or the same scale here at the y-axis to make it like comparable between both. the most interesting thing we can take away from these graphs, without like talking about everything, is if we compare the vertical velocities of the diurnal cycle and the semi-diurnal cycle for the maximum amplitudes, which is like the same amplitude, we can see that the maximum vertical velocities are much higher for the semi-diurnal cycle than for the diurnal cycle, which is potentially related to the elastic part and less time to relax between the force changes than for the diurnal cycle. Another interesting part we saw is that the horizontal velocities have a double peak per cycle, which is due to the up and down movement. You have one peak is on the top surface and the second maximum velocity peak is on the bottom surface. So that explains these quite nicely. I think that's it for me for this. If you have questions, I'm happy to answer them afterwards. Thank you very much.
Thank you, Astrid. That was really interesting. I think we move over to the next office at Swansea University and hand over to Glenn Jones, who has just finished his fellow position at Swansea using passive seismic noise methods to image beneath the Greenland ice sheet, and he's now working on modeling rift propagation on Larsen Sea ice shelf. And with that, over to you, Glenn.
Thank you, Rebecca. I'm just gonna, oh, no one wants to see that. I'll just share my screen. Can everyone see the screen?
Yeah, that looks good.
Brilliant. So yeah, so today I'm going to be presenting some of my work from my fellowship, where I used passive seismic methods using noise to characterize the upper crust beneath Greenland and its implications for ice sheet dynamics. But before I begin, I'd like to acknowledge my co-authors, as well as the European Regional Development Fund and Welsh Government for funding this work. So the motivation, conditions at the base of a glacier or an ice sheet are a dominant control on ice flow, and can actually have quite profound effects on ice mass loss and obviously ice, how it flows. So these features work on a number of different spatial and temporal scales, and this is shown in this graph on the right hand side here. And we can see that there's a number of overlap and interactions between these different tectonic regimes or sort of small scale or local scale features. So one sort of example of that can be kind of seen here in this ray diagram. So we've got a cross section through Greenland, close to the northeast Greenland ice stream. Now we can see that it's all well behaved up until the bottom over here. And at the bottom we have effectively soft, malleable ice. And obviously the basal conditions here, water content, geothermal heat, as well as topography. And all of those things are obviously geologically informed and obviously have worked on different length scales, can lead to this soft ice and obviously interact with each other. And unfortunately, it's a major unknown in ice sheet models. And so our estimates of sea level rise. And this is just a kind of example of a series of geothermal heat flux models for Greenland. And what we can see is the dark colors represent low geothermal heat flux and the yellows represent high heat flux. And what we can see is quite a difference between each of these models. And so that can kind of lead to these kind of large uncertainties in our estimates of how these ice dynamics systems work. So the goal is to quantify the relationship between ice flow and subsurface geology. Now, monitoring glaciers, we've kind of traditionally used satellites and airborne radar, and that's kind of revolutionized glaciology. It's allowed us to kind of get accurate estimates of ice flow velocities, basal topography, ice thickness, and this is just an example of ice thickness from the bed machines model. However, these methods are limited to really only ice properties. They give us very limited information about the basal properties and the actual geology itself. Now, historically, passive seismic or earthquake seismology has been one of the main methods of choice to determine the Earth's structure. And it's been highly successful over a number of decades, producing high resolution images of the Earth's structure. And this is just a geological map of Greenland. And we can see that a lot of the geology is obscured by the ice, and the red triangles are the seismic stations in Greenland. Now, we were fortunate enough that in around 2012, there's a significant increase in the number of permanently deployed stations in Greenland. So this makes it ideal for us to start using new seismic techniques in these regions. So the aim of the project was to use seismic ambient noise to characterize the geology underneath Greenland. And to do that, we're going to be using Rayleigh waves. So Rayleigh waves are surface waves, and they have elliptical particle motions. And the particle motion travels in the opposite direction to the wave. The particle motion will become important later on. Now, the wave amplitude decays with depth, and the Rayleigh waves are sensitive to the near surface structure of the Earth, and so they're ideally suited to characterize the crust and upper mantle. Now, what we can do with these images, well, these Rayleigh waves, we can produce either 1D profiles or 2D slices to the Earth. And this is just an example of a 2D tomogram of seismic shear wave velocity through Greenland at 10-kilometer depth. Now, unfortunately, methods using earthquakes are limited to resolutions of greater than 10 kilometers. In the last 20 odd years, there's been quite a revolution in passive seismic methods and imaging, where we can use the actual noise of the Earth, and that's led to significant improvements in resolution. And this resolution is controlled by the station separation. Now, unfortunately, in Greenland, again, the resolution is limited to 10 kilometers due to this station separation. So an alternative approach is to use the actual elliptical particle motion and the actual change in this elliptical particle motion as a function of period. So I'm going to just describe now how we do that. So ellipticity, or the ratio of the horizontal to vertical component of the Rayleigh wave displacement, is sensitive to the Earth structure beneath the station. And we can use ellipticity to produce 1D profiles of seismic velocity and density. And we can see that just in this graph over here. So what we have on the left-hand side is a depth profile, where the red is the true model and the black is the recovered model from the data. Now, the data used are these circles, the mean values of ellipticity computed from earthquake data. And what we can see is that we can recover this model very accurately at depths of greater than 5 kilometers. But unfortunately, we're unable to calculate or estimate this region at the near surface. Now, obviously, that presents a problem for us, because obviously that's the region I'm interested in, and obviously that's an issue. So what we can do is we can actually use the ambient noise. So if we can extract Rayleigh waves from the noise, then what we can see is we can actually recover this upper 5 kilometers accurately. Obviously, if you combine both, then we can clearly recover the first 30 or more kilometers of the crust. So clearly, noise measurements are essential if we are to characterize kind of features underneath Greenland. So what does seismic noise look like? This is what it looks like. And it consists of a number of different seismic waves, a number of different sources, so earthquakes to ocean wave interactions to waves crashing on the shore. And clearly you can't really see much in this image over here. But by taking a series of overlapping power spectra, we can compute a probability density function. And this is effectively a probability density function or spectra of the time series I just showed you. And what we can see is there's a number of kind of distinct features in here. So at periods, very short periods, we end up with this kind of green region here, and they're local earthquakes or ice quakes. And then we can start seeing this kind of hump around this region here. And these are known as secondary microcysms. And if we think of the periods that we were interested in, so from the previous slide, we were interested in periods of 1 to 10 seconds. Clearly, this secondary microcysm is what we're interested in. Now, these secondary microcysms are produced by ocean wave interactions. So as two waves crash against each other, they produce a pressure pulse, and this pulse propagates through the water column and then converts to seismic waves as it interacts with the sea floor. So now that we know what periods we're interested in, the question is, how do we extract this information? And the way we do that is we can use the polarization properties of the actual Rayleigh waves. So on the right-hand side here, we've got an idealized Rayleigh wave particle motion. So it should be planar as we look at it front on. This should be fairly vertical and have very little inclination. So if we can use those properties, we can effectively extract the data as we want. And the workflow to do that is to effectively window the data, and the length of the window is dependent on the frequency of interest. We then transform that data in the time frequency domain and effectively compute do a principal component analysis on the three component seismic data. Once we have that, we can then have the polarization attributes, and we can also calculate what the ellipticity is and perform various quality controls. Now, the polarization information can actually give us some information about where these the sources of these Rayleigh waves are. And in the next figure, I'm just showing you an example of a month's worth of data. And on the left-hand side, we have a polar histogram. At the center, we'd have the seismic station, and radially, we have the frequency. And what we can see is there's a really strong kind of bright patch pointing towards the southeast. Now, if we look at this on a map, so if we effectively overlay this over this triangle here where the station was, we can see it's pointing in this direction. Now, the contours is air pressure at sea level, and that's a very good proxy for storms. So we can see that the vast majority of the signals are all coming from this region in the North Atlantic, as we would expect. So that gives us a bit of confidence that actually we're observing these secondary microcysms which we are interested in. And that can also be seen like this histogram here. It's just the summation of the polar histogram bins. Okay. So what do we do with these measurements? So we collate all the ellipticity measurements and we compute some summary statistics. So the mean and standard deviation, and they will be used for the calculation of the Earth structure. And some interesting observations here. So these are plots of annual average, annual statistics for an off-ice station and an on-ice station. And the first thing to see is that the observations are very consistent over the different years, which is very reassuring for us. But what we can see is that the off-ice station behaves relatively flat. So So there's no real kind of significant variations. But if we look at the on-ice station, we can see that there's quite a significant deviation. And of particular interest is effectively the ice produces this region down here, and the kink or the kind of turn in the graph effectively is dependent on the ice thickness. So the thicker the ice, the more towards the right, or the longer the period which is affected. Now, this linear feature here is quite strange, and it's to do with effectively with the near surface effects of the ice. And the other thing to take note is, as we sample the actual ice itself, uncertainties start to grow. So that's obviously a challenge for us. So what do we do with these data? So the first thing we did was a quality control, and we found that by removing effectively data with uncertainties greater than 0.2 in the ellipticity, that stabilized our inversion. And also you should note that these are actually just periods which are actually sensitive to the ice itself. So these aren't periods which are sensitive to the actual geological structure underneath the ice. So we fixed the ice as a single homogeneous layer with the thickness taken from the bed machines model, and we gave it a various, so the VP was 3.8 kilometers, density 0.92, and PS of 1.94, and I think they're pretty standard values. And then what we do is effectively we search over the combination of depth and seismic shear wave velocity, and we search through those using a Monte Carlo approach to quantify our geological structure. So what I was showing here is basically the blue dots are our measured data, and the green line is the original model. So this was the best model available for Greenland at the time. And the red line is our best fit model, with the black region representing the best, the models within 20% of our observations. And in depth, what that looks like is the gray is the search space, our parameter space, and obviously the green is the actual original model, and obviously the same close. So the red again is the best fitting model here, and the black is the best models within 20% of the best fitting model. So we can see that, number one, our models fit the data better than the previous model. And so what does that look like spatially? So spatially, what we have is is effectively this image here. And what we can see is that the low VS regions correlate with high heat flux as proposed through the Iceland hotspot track. And that's seen in this geothermal heat flux model over here. So we can see a strong correlation or comparison between these two models. And the interesting thing is that this model over here was from Martos et al. Was computed actually using gravity and magnetic data, not seismic data. So it's nice to see that our model closely resembles a independently computed a geothermal heat flux model. So regions of high heat source, we believe are regions for alteration of rock and till production. In this particular case, around this region here in the center of Greenland, close to the northeast, the initiation point of the Northeast Greenland ice stream. And other correlations of these low VS regions, which are indicative of warm regions, is water in the Northeast Greenland ice stream, and also enhanced ice deformation, as I showed earlier on. So in summary, we successfully applied new seismic ambient noise ellipticity methods to characterize the upper 5 kilometers of Greenland. Measurements of Rayleigh wave ellipticity from noise, so we were able to extract these ellipticity measurements from noise. The results we obtained were independently verified with the work of Martos et al., their geothermal heat flux model. So our regions of low VS correlate well with that. And also these regions of low VS correlate with regions of basal melt, and also the proposed onset of the Northeast Greenland ice stream. And also, yeah, geothermal altered rocks as a source for enhanced, for till, for potential enhanced ice flow as well. So an advert for next week. So we have Andreas Riviere, who will be giving a talk titled Current Status of Chilean Glaciers and the Discussion of a Glacier Law. Thank you.
Thank you, Glenn, and thank you to all 3 speakers. We are now at the stage to ask any questions. So anyone who has a question, please put it in the chat or raise your hand so we can navigate to unmute people. Maybe I can start off with a question because I don't see anyone having a question right now for, for Astrid. Can you say something about like the limitations of your modeling or the model you use compared to other models?
Limitations are, there are some limitations, yeah. There's, I cannot compute a reasonable result for very long ice shelves, like greater than, I think 15 kilometers. It just doesn't give any results, which I think is not a problem because for like free floating ice shelves, like unpinned ice shelves, we don't really have any longer ones. Additionally, I think there's still a lot of possibilities in there that could be explored, which I haven't explored yet. But I don't really, I have struggles with the higher viscosities for the tidal signal. But other than that, I haven't seen any problems yet.
Okay.
Or limitations.
Thank you. There is a question from Roger. Do you just want to ask the question, Roger? For Alex, by the way.
Yeah, sure. Well, thank you to all 3. Very much enjoyed that, especially Glenn's subject area close to my own heart and experience. But specifically for Alex, what is that submarine ridge made of? Do we know? And yeah, how vulnerable might it be to later parts of that chain you showed us?
I'm afraid I'm going to have to give you a bit of a cop-out answer because I'm not a geologist of any sort, and tell you that I don't know what the ridges consists of. My understanding is that it's been there for a long time and isn't under any threat to its own stability. But I think I'd have to defer that to someone who knows more about beds than I do.
Okay, fair dues. I was just thinking it might be very different if it's an appropriately angled, hard bedrock material, crystalline basement material, as opposed to some sort of accumulated sediments or something like that. And you know, those later steps in the chain are going to go in very different directions. depending on all that lot. But yeah, I'm sure someone's getting a grip of it.
Yeah, I mean, there's certainly evidence that it's of sediments there. That's one of the kind of key pieces of evidence that shows that Pine Island retreated from that ridge. Its grounding line in the 40s or so and earlier used to be on the top of that ridge, and it retreated from that in the after the 1940s. And some evidence is a paper by James Smith from 2017, which looks at the sediments there. But I don't think it mentions about the crystalline structure, at least not that I remember.
Okay, thanks a lot.
We also have a question from Olga. Do you just want to unmute?
Yeah, thank you. Great talks. All three talks are great. And I have questions to all speakers. So you guys decide like the way how you would like to receive them. Or Rebecca, maybe you can moderate.
Well, just go ahead. Like
Okay,
whoever.
so then in the order you gave talks, the question to Alex, how did you force your model? What did you use as a forcing?
Yeah, that's a really good question. So in the idealized simulations, we restore the ocean far from the ice shelf to some idealized temperature and salinity profiles far from the ice shelf, and they're like approximations to the temperature and depth profiles that you see in practice. And in the realistic simulations, we used realistic temperature and depth profiles, and so the simulations are essentially forced by the competition between buoyancy fluxes that come from meltwater from the ice shelf, and they work in competition against that boundary restoring.
Any surface forcing, I mean, wind stress or anything at all like that?
There's no wind stress in the simulations, and I appreciate that that's quite important, particularly in the realistic simulation.
And I suspect no sea ice either, right?
No sea ice. Yeah, we're just
okay.
trying to keep it as just that competition between boundary restoring and buoyancy fluxes.
All right, thanks. And then a question to Astrid. I didn't exactly get your steady state results, or rather I'm quite puzzled why you have different results for steady state simulations for viscous rheology and visco-elastic. Specifically, as you started your talk saying that the elastic component is because of the time variable. In steady state, there is no time variation whatsoever. So I'm a bit confused what the effect of elasticity in steady state might be.
Yeah. First of all, like I have to run several iterations for like the for the viscous and for the viscoelastic problem, but with no change of the forcing, because it takes some time for the model to actually calibrate to a like where it doesn't change anymore. So if I don't change the forcing, that's like a near steady state approach. The differences you were seeing in the viscous and between the viscous and the viscoelastic model, I think are predominantly because it's steady state and I don't have any forcing. It's probably predominantly because of the difference in the bottom boundary. So for the viscous model, which is quite common, I used a zero velocity, normal velocity acting like in normal direction. There's no velocity at the bottom of the ice shelf, while at the viscoelastic model, I implemented the buoyancy force together with the displacement correction. So I think that causes a slight change, especially in the vertical velocity.
So effectively, these are two different problems, what you're solving then. It's kind of comparing apples and oranges because of the bottom boundary condition. Is it correct?
A little bit, yes, it is indeed. But I think what we can see that the magnitudes are quite similar. There's no weird, like one is extremely higher than the other. So I think in that sense, it also shows, I think, because for a long time, for the viscous model, they use this bottom boundary for ice shelf calculations. So it shows that this is compared to the visco-elastic model with the proper boundary, bottom boundary, it's a bit overestimating the velocities.
I'm not exactly sure because, yeah, it's just different boundary conditions, so it's kind of difficult to compare the results if the formulation of the model is quite different. But okay, thank you. In a question to Glenn, I guess it's more kind of, could you speculate about the consequences of your results, what you showed on your last slide, that what you retrieved velocities, the magnitude of velocities, and the related geothermal heat flux. So the magnitudes of those differences, what you have, say the geothermal heat flux varies between 50 and 70 milliwatts per square meter, something. But the most prominent ice stream, which is Negus, and which is attributed to the effects of geothermal heat flux, it's pretty much the only one. But the magnitudes are not that substantial. It's not like orders of magnitudes of factor 3 or 4. So why then we don't see that many ice streams in Greenland? Can you speculate, or it's way outside of?
Yeah. I don't know. Certainly sort of what our models were showing can be if we kind of go further. So the model I showed was kind of a couple of kilometers depth. If we go we can start seeing slow velocities in and around the or slower velocities, which are kind of comparable with damaged or altered rock. So part of, and also some other work has been done on the Northeast Greenland ice stream, and they've seen this potential, till type of layers. So my speculation is that we may have just sort of remnant damaged rock from the Icelandic hotspot traveling, or Greenland traveling over it, and that rock might be sort of just close by. That's just allowing that to sort of flow. But also I think there are other things like geometry, topography and things like that, which will probably play as an important, if not more important role than potentially the actual heat flux alone. Yeah. That's my,
no, that's great. Thank you. Yeah, and thank you all great talks. Thank you, guys.
Thank you for these questions, Olga. Do we have any more questions? Okay, I can't see anything. In that case, I think we'll be after 10 o'clock anyway. I think I want to thank all 3 speakers for today. Thank you so much for sharing your results and your time. And I'm looking forward to next week's talk by Andreas, and yeah, see you all next week.
Thanks very much to all the speakers. They were fantastic talks.
Thanks, Rebecca. Thanks, Katie.